Welcome to the lesson on Hessian matrices and second derivatives. We're going to use several different techniques to find the second derivative of various functions involving vectors and matrices. You usually don't see the Hessian matrix in a calculus course. It's basically taking the gradient of a function from Rn to R and then taking a gradient of the gradient basically. I'll show you an example in the next slide, but let's just look through what I mentioned here. The Hessian matrix is a square matrix of second-order partial derivatives of a scalar valued function from Rn to R. It describes the local curvature, so it's not the slope, but it's sort of a generalization of that local curvature of a function of many variables. It was developed by a German mathematician, Ludwig Otto Hesse, named after him. There's different notations. We're going to use either this novel squared f or h sub f, which I like because they both include the name of the function in the notation. And then here's the structure. Assuming all the partials exist, then the first row has all the combinations of partial derivatives involving x1, and then the second row is all the partials involving x2, and so on until you get to the nth row, and then that has all the combination of two partial derivatives involving xn. So let's look at an example in the next slide. If the second partial derivatives are all continuous of a function, the Hessian matrix is a symmetric matrix by the symmetry of the second derivative. This is a general result. The order can be shifted here and you still have equality. And then that implies that the Hessian equals its transpose. The Hessian matrix of a function f is the Jacobian matrix of the gradient of the function. And we'll use that fact in our example. So you have a function from R3, x1, x2, x3 into just R. This is a scalar when you plug in all the numbers. So first we take the gradient, and it's pretty simple. We take the partial with respect to x1, then with respect to x2, and then with respect to x3. Let's just take an example of one of these. The partial of this with respect to x1 is 3 x1 squared, x2, and then these don't involve an x1, so they're all have a partial derivative of 0 with respect to x1. All right, and then we get similar things for the other two rows. And then knowing that this is the partial with respect to x1, we can use that to get these here. We just take the partial with respect to x1 again, and we get 6x1. Then the partial with respect to x2 of this, and it's 1. Then, of course, the partial of this with respect to x3 is 0 because there's no x3 in this. Okay, and then we do the same procedure here. We have, knowing that this is the partial with respect to x2, we take the partial with respect to x1 to get this first term here, and that's just 1. The partial of this with respect to x2 a second time, these two drop out, and we get 6x2. And then the partial of this with respect to x3 is 1. And similar for the third row. So you can see the symmetry here, 1, 1, 0, 0, 1, 1. We knew that from this result, but this example bears that out. Okay, let's look at second derivatives of vector-valued functions. Consider functions that map from Rm to Rn, where m and n are greater than 1. Various approaches are possible, and I'm going to take an example and go through the different approaches. The first approach is going to use something known as the third-order tensor, which is really a multi-dimensional array in this particular case. So for f from Rm to Rn, the second derivative can be expressed with the following third-order tensor. So t, I, j, k. I stands for the functions, and then j and k are the variables. And so basically you're taking each function and then all the combinations, taking two at a time of the different variables, and you're taking that partial derivative. And so in our case, there's two functions, and then there's two variables. So that would be a 2 by 2 by 2 tensor. It's sort of a 2 by 2 matrix, and then another 2 by 2 matrix. So you can almost think of it as a three-dimensional object. So let's actually compute this, and we'll do that on the next slide. I copied our function down here at the bottom, so we have that to refer to, and here's our tensor notation. So we want to get we're going to get two tensors, one for the two parts of our tensor. The one is, or a slice, I guess it's called. One is for the first function, one is for the second. And to get this, for the first one, we need to take the partials with respect to involving x, the two partials involving x, and then the two partials involving y, both with respect to f1. So that's what I've done up here. We can look at a few of these. We take the partial with respect to x twice. It's 2xy and then 2y. We take the partial with respect to x, it's 2xy, and then with respect to y, it's just leaves us with 2x. Then by symmetry we get this. Then this one here, if we take the partial with respect to y twice, first we get x squared and then we get 0 because x squared doesn't involve a y. Then we just plug these two into the first row and these two into the second. We do the same thing for the second function. Let's just look at a couple of these. So if we take the partial with respect to x twice of this, first we get y cosine x, and then we get y minus sine x. If we do this second one, we take the partial with respect to x, we get y cosine x, and then with respect to y, and we get just cosine x. Then by symmetry, we get this. And if we take the partial with respect to y twice, first we get sine x, and then we just get 0. So we plug those in. Then our tensor, I've drawn it this way. I mean, you could, if I could draw in 3 dimensions, we could put this one first and then this one behind it, and you would kind of have a 3-dimensional object, but this will do. And that's our answer using tensors. Now we're going to do it in 2 other ways, and I'll show you that on the next couple of slides. Another approach is to form an array of Hessians, one for each component of our function, f. Now you noticed in our example we just had f1 and f2 as the components, but if you're mapping to fn, then you would have n components of your function, so the second derivative would look like this, a Hessian for each component of your function. So in our example, we just have the 2, as I mentioned. We've already done this computation on the previous slide. So this is the Hessian for f1, and this is the Hessian for f2. And then our second derivative is just this tuple of 2 Hessians. We have one more way of doing this, and I'll show you that on the next slide. Okay, we have one more approach. We're going to take the Jacobian of our function, which will give us the first derivative. Then we'll vectorize the Jacobian and take the derivative again, and that'll give us the second derivative. So that's what I've done here. I've copied our function down. This is the Jacobian. We take our function f1 and we take the partials with respect to x and y. Get this, and then take f2 and take the partials with respect to x and then with respect to y. We get the second row. Then we take the vec of this. We get this here. We take the first column and then the second column. And then this is just a mapping from, effectively, this is a mapping from R2, our x and y, to R4. So we can apply the Jacobian again. So we take the partials with respect to x and y for each row here, and that's what I'm showing. Okay, so it's the same information that we got in the last two approaches. It's just jumbled up in a different arrangement. I think that the second approach seems to be the cleanest, where you just take the Hessian of each function and then you can just line them up in a row and have your second derivative. If we're presented with a function in terms of vectors and matrices, as opposed to the internal details as we saw in the previous couple of examples, it may be better to use the differential approach based on the Fouché derivative to find the second derivative. And I have one example of that here. So we'll take our function f of x equals x transpose ax, where x is a vector in Rn and a is a constant n by n matrix. We already took the first derivative. That was example 4 from the previous lesson. So we have that as a starting point. We just need to take the derivative a second time to get the result that we want. So I let g of x equal f derivative, and then we're going to just do the differential approach on the g, and that'll give us our solution. So we have g of x plus d of x minus g of x. Then we plug in x plus d of x for x. So I've done here, and we subtract g of x. Then we multiply out, taking the transpose first and then multiplying. So x transpose times a plus a transpose plus d of x transpose times a plus a transpose, then minus this term, then this term and this cancel, and we get this here. So this is almost the form that we want. We'd like to have the dx on this side. The workaround is to note that the solution that we found is a row vector, and the format that we used to is a column vector, but they have the same components. So this effectively gives us our answer, and we can conclude that a plus a transpose is the derivative of g, and then therefore the second derivative of f is a plus a transpose. We could solve the problem from the previous slide using the product rule and the differential, which I'm describing here. So another approach is to note that the second differential of f is a differential of the differential of f. So we can find df by taking this differential a second time. From example 4, we also computed the differential, this thing here. So using the product rule, we have the second differential of f of x equals the differential of f of x. So plug this in here. Then we use the product rule. So it will be the derivative or the differential of the first times the second. And then the first term times the differential of the second. This is just a constant, so you get the second differential of x, which is 0. It's a higher order term, that's 0. And so you just get this here. But we still have the task of extracting the second derivative of f from this expression here. So we need to do a little bit of work to extract this. We know from the previous solution that it's a plus a transpose, but we need to figure out why that's true. So to that end, let f of x be any function that has a vector input and outputs a scalar, such as the problem at hand. By definition, the second differential of f equals the differential of f. Then I just plugged in the representation for the differential of f, which we stated much earlier in another lesson. So you have this here. Here, in this case, dx is treated as a constant, since it's independent of x. And so we can move the x out of the differential like this. So in other words, this is equal to this. The differential of the gradient is the here, and that's the basically the second order gradient of f of x dx, where this is the Hessian. Then we substitute back into here. We just get the second differential of f is the Hessian times the x transpose, where it equals this here, just taking the transpose, get the transpose of dx times h times dx. So for problems that fit this condition, which is the case for us, excuse me, the Hessian, or the second derivative, can just be read off. And you notice we have the same form here and here. So the second derivative is a plus a transpose. So we've shown that in a second way. So this is a general formula for functions that map from Rn to R. The second differential has this format here. So if you can use some other methodology to get your second differential into this format, then you can just read off the second derivative, which is what we've done here. So this is the last example in this lesson. And this lesson is the last lesson in my series on vector calculus. I'll follow up with another series on the Einstein notation and the related topic of tensors, so stay tuned for that. So our problem is, let me point to it, given f of x equals x cubed, where x is an n by n matrix of variables, find the second differential and the second derivative of f. In a previous exercise, we found the first differential, so we can make use of that. And we also need to find the differential of x squared in our computation, so I'm showing you it here. It's just applying the product rule to x times x. So here we have the second differential of f, which is the differential of the differential of f. So in other words, the differential of this. We need to use the product rule in each term. So we'll first do it. Each line applies to one of these terms. So we'll do it on the first one here. We need the differential of x squared, which you've computed. I put that in red, and then times the second term. Then plus the first term times the differential of the second. Then we go to the second line, and it's the differential of x times the second term. I combine these two into the one term. And then the first term times the differential of this. We need the product rule, which I've applied and expanded out here. Then the third item here, we take the differential of the differential of x times the second term, and then dx times the differential of x squared. So we plug this in here. So all of these second differentials of x are 0. It turns out the explanation is not so simple. You may just assume it's 0, but it actually has to do with differential geometry. If you're interested in the explanation, just go to an AI program such as ChatGPT or Grok or DeepSeek and ask why is the second differential of x equals 0, and you'll get an explanation. But again, it goes beyond the scope of this course, so I'll just ask you to accept that it's 0. So this is 0, this is 0, and this is 0. And then that leaves us with 6 terms. We can combine those, which I did, since there's duplicates. Then I just factored the 2 out. So this is our second differential. And then the second derivative, if we view it as a bilinear operator on dx and dx, it's equal to this, basically. If you go to some text, or if you go to an AI program to ask for the solution here, they'll often assume that these two dx's are not the same, which I guess is reasonable. You might want to have a bigger differential on the first time around, and then when you do the second differential, maybe you want this to be bigger, and so they'll use like h and k, and then you don't get all this consolidation. You get 6 terms with various combinations of h, x, and k. I didn't do that here. I took a little bit simpler route, but I just wanted to note that. So we can go further. We can vectorize this. We can vectorize this and get another form of the solution. It's rather complicated, but it exercises some of the things that I wrote about in my previous series of lectures on matrices. So you can skip it if you like, but if you want to get some practice with the Kronecker product and the VEC and some of those things, then have a look at the next slide. So as I noted, as a further exercise, we can vectorize the second differential. And the process is we vectorize each of the terms. This was our solution from the last slide. We apply theorem 72. Remember, we've used that before. I wrote it down here several times, and then collect terms to get the final solution. All right, so for the first term, we vectorize this, and I left the 2 out. I'll bring it back at the end. We vectorize this here. So I put an identity matrix here, just so we can get it in this form. And that gives us this. I just wrote out the x squared, is it dx times dx. And then the vec of dx we can write this way, and then apply this. We get this here. I just wanted to get a vec dx, that's why I went this further step. And then you plug this into here, and you get this awful looking thing. So the second term isn't any prettier. You have this here. At least we have the 3 matrices. Remember, dx is a matrix. However, to get it in a form that where the dx is at the end, I needed to combine these first 2 together, and then dx, and then multiply by the identity. And then when you apply this here, you get the Kronecker product with dx times x times the vec of the middle, this middle term here, dx. Get that here. Now we need to do this one, so let's go to the next slide. I copied our formula from the first expression for the second differential here. And we already did the vectorization of these 2. We need to do it for this one. So I wrote it here. Then I put in the identity. So this is equal to this. But now we can use our formula. We get x transpose Kronecker product was I. The vec of dx squared, which I wrote as dx dx. And remember we computed this on the previous slide. So I just plug that in here. We get this. Then we take the 2 results from the last slide, this result, put the 2 back in here, and then we have the vec of our second differential equals this horrible looking thing. We also have this identity from the Kronecker product earlier in my series on matrices. Give you a second to look at that. It's just saying take the A times the C and the B times the D and take the Kronecker product, and these 2 are equal. So that helps a little bit with this. We can apply that here. We get the I times the I dx times dx. So we get, applying this here, we get this. Second one we leave alone. Then we can apply this to to this one here. We get this. And so this is the vectorized form of the second differential. Okay, so that's it, at least for the technical part of this lesson. I have another slide following this on further study and a bunch of references. On this slide I have some references for further study. There are several books and internet sites that provide lists of known derivatives of functions. I mentioned this in my last lesson, but I'll mention it again. So there's the Matrix Reference Manual by Mike Brooks. And if you go to this section on calculus, you'll find some computations for derivatives involving matrices and vectors. Then there's the Wikipedia article on matrix calculus. If you scroll down quite a bit, you'll see that they have a number of tables that'll, again, give you formulas for the derivatives of functions that involve vectors and matrices. Then there's the Matrix Cookbook, and you can download this from the Internet Archive. It's freely available, as are these other two. Then there's an MIT course that they've made freely available. It's called Matrix Calculus for Machine Learning. So a lot of the ideas and concepts I've used in this lesson and several past lessons are based on some of these lectures from here. So I'll recommend this. Then I also use some information from this paper. It's called A General Introduction to Matrix Calculus by Magnus. It's very technical, and in spite of the name, I don't think it's easy to read. I took, as I say, some of my information from lessons that I provided, especially on the Matrix series, the series before this, from this book, but I needed to add some additional explanation. And then this paper, in turn, is based on a book by Magnus and another Neudecker, another person. And the book is even more complex than the paper. But if you really wanted the full story, I would go to this book. And it's hundreds of pages long, but it has extreme detail about matrix differential calculus. Okay, so I'll cut and paste this into the information for this video, so you don't have to copy down these links. You can just click on them in the information to the video.